do this.
Come on. Then you got ube, un grito.
No, they're gonna be in math too on Friday.
Yo me escape. Yo me
Strong.
They almost on the list. Notebook, it's not. Every questions that are not in the notebook.
No, I'm just gonna take Colsey. I might as well. Where's Sarah? Should I go Sarah or Coles?
Oh.
Sarah.
I
Right
love my
here.
class. I love my table.
See right there? Okay, because I'm on his.
All right, here we go.
My table was a bunch of.
Where did we leave off yesterday, or the day before?
Give me a second.
Geometry.
Did we get bond angles and all that?
We talked.
We're talking about like bends, the bends, the trigon,
Trigonal pyramid?
yeah,
I didn't tweet it. I didn't.
linear,
And then
So-
a little bit.
What's this shape right here?
That's for, I can see for.
Is that tetra? Tetrahedral?
Tetrahedral, right? Tetrahedral. Okay.
Sorry, Larry's Spanish.
I like that one more than the other one.
See this one better?
Yeah, I can see that
A
one.
larger, okay. So this is methane. Let's just pretend it's methane. Let's say that's a carbon. These are 4 hydrogens. So this is tetrahedral. The bond angles are 109.5 degrees. Okay. The important thing that we'll come back to here in just a minute is that this is a symmetrical shape. Okay. Now, if we took off a hydrogen and only had 3, let's say now this is a nitrogen in the middle. Okay. These are 3 hydrogens, and this stick up here is a lone pair. All right, so electronically, in other words, the 4 electron domains or regions of density are still tetrahedrally arranged. So this is still electronically tetrahedral, but it's now molecular geometry is a trigonal pyramidal. Okay. Trigonal pyramidal. Some people say trigonal pyramidal. Okay. Now, if we have, let's now say, for the sake of conversation, that the central atom here, this black one, is now an oxygen, and these are 2 hydrogens. So now we have water, right? Okay. So we have 2 atoms, 2 lone pairs. So we still have 4 regions of density. So electronically, that's still tetrahedral, but molecularly, this is a bent geometry. Okay. This is not symmetrical, all right, for reasons we'll talk about in a minute, and neither was this one. Okay, there's no symmetry there. There's not any symmetry here. But if you have 4 identical atoms arranged around the central atom, then it is symmetrical. Okay, we'll come back to that in a minute. All right, what did we say about carbon dioxide yesterday? Oh, let's talk about bond angles for just a second. This bond angle is 109.5 degrees. If you take off one of the hydrogens, this lone pair takes up a lot of space, and it makes these other 3 squeeze together just ever so slightly. All right, so we'll have about 107 degrees here. Take off another one. This one right here. And they're going to squeeze together just a little bit more. You have 104.5 degrees. Let's see. Back up here somewhere. So what we're doing here is filling out this piece of paper, right? A blank version of this piece of paper will be given back to you on Friday for a quiz, right? We moved that to Friday. Was that already? So move that. to Friday. There you are. So you've got the actual quiz in front of you right now, right? So everybody should make 100 on this, correct? Right. Filling out all the answers. Good. All right, carbon dioxide, let's talk about it. So how far did we get with it? We drew the structure, right? Then a yes. Did we decide what its geometry was?
Geometry is
Linear, okay? So we know that because we count the regions of density around the central atom. There's 2 of them. There are 0 lone pairs on the central atom. So if we look at this chart, 2 regions of density with no lone pairs is electronically and molecularly linear. The angle of a straight line from your geometry class is what? 180 degrees, right? Okay. So it looks something like that. We'll explain why we got this clownish looking thing. Okay, but that's supposed to represent the double bonds. Okay. Kind of see what we're talking about. Yep.
How come like the bonds are almost opposite, where one goes up and one goes to the side?
That's got to do with the arrangement of the atomic orbitals. We'll talk about that in just a minute. We'll talk about hybridization and pi bonding and stuff. We'll get back to that in just a minute. All right, so carbon dioxide looks something like this. Of course, these are just models, right? It's not actually what it looks like, but it's close. Geometrically, they're the same. All right, so the angle of a line is 180 degrees. And this would be symmetrical, particularly this one, because the oxygens are the same on both sides, so there's symmetry here. Okay. All right, now, questions so far? What's next on the list?
Hybridization.
Okay, hybridization. Does everybody know what a hybrid is, biology class? Some things that are similar but different, right? They cross to make something else.
Yeah.
So you've got a, what do they have to be? Let's see, same genus, different species. Okay. So most common or classic example is a donkey and a horse. You breed a donkey and a horse, you get a mule. Okay. So mules have all kinds of special qualities about them. All right. One being that they can't reproduce themselves. That's the biological result of a hybrid. So the point of hybrid, the definition of a hybrid, is the mixing of 2 things that are different but yet similar, right? So chemistry, we have this thing. We have a couple of things we throw the word hybrid in, but one is hybridization of orbitals. If we remember the it's not working. Sorry, here we go. Okay. So if we remember the orbital diagram of carbon, it would look like that, correct? Okay. So the problem with that is the 4 valence electrons of carbon are right here. Those 4 valence electrons are individually being shared with the single hydrogen electrons of these 4 hydrogen atoms, right? Okay. We've already said that that makes a symmetrical tetrahedral shape. That's been experimentally proven. Okay. So the question is how do you get 2 electrons that are already paired up with each other in an s orbital and 2 unpaired electrons in a p orbital to make 4 single covalent bonds that are all the same length, same angle, perfect symmetry. Something has to happen, okay? Now that something gets really complicated, okay? And how you get from point A to point B right here is way, way, way past this class, all right? But here's what happens. Here's the final result of what happens, okay? The core electrons stay just like they are. These four orbitals right here hybridize into four identical orbitals that we call sp3 orbitals, and they're still on the second energy level. And one electron goes in each one of those. So now you have four electrons in four separate identical orbitals so that they can be shared with four identical hydrogen atoms and end up having four identical symmetrical single covalent bonds. Okay. How it gets from point A to point B is way past this class, and in fact, I don't think it's even completely understood by anybody. I think that you still don't really know how it does it. It's just one of those things that it has to do it, or that wouldn't make any sense. Okay. So here's all we have to know. Okay, at this level of chemistry, we just need to know the type of hybridization that's occurring. We don't have to know why or how or any of that, just the type. Okay, and it's real easy to keep up with. If you look on this chart, methane is a 4-0, right? 4 regions of density, no lone pairs. 4 regions of density means you got to have an s and 3 p orbitals. Because you got to have 4 hybrid orbitals for every region of density. You got to have one to one. So if you got 4 regions, you got to have 4 orbitals to hybridize. So that means you take an s and 3 p's. Okay, and that's called sp3 hybridization. All of the 4 region molecules have sp3 hybridization. The 3 region molecules have sp2 hybridization. You need an s and 2 p's to make 3 regions of density. Okay. If it's 2 regions, you just need an s and a p to make 2. So that's sp hybridized. So all you gotta do is count. Once you've already counted, you're counting the regions of density already. Okay. And you just have the same number of hybridized orbitals as you do regions of density. So that matches 3, 3, 4, 4, matches up. Okay, so that part's pretty simple. What's really going on here gets really complicated past high school. But so 4 regions of density. This is sp3, and that's a superscripted 3. It's not a cube. It's not a mathematical thing. It's just a counting label, sp3. This has 4 regions, so that oxygen is sp3 hybridized. 4 regions, so that nitrogen is sp3 hybridized. This carbon only has 2 regions, so that carbon is sp hybridized. And that's all there is to that. You just have to be able to count them and say what type of hybridization this is. You won't be asked to explain it or draw it out any more than that. What's next? There. All right, a minute ago we mentioned that this was symmetrical, right? Okay. So let's look at it individually, individual bonds here for a second. Carbon, hydrogen, right? Just looking at those 2 right there. The carbon's more electronegative. So they're having a tug of war. That stick right there represents 2 electrons that are being shared. But they're not being shared equally because carbon is more electronegative. It's going to pull on them. Okay? It's like a tug of war. The carbon never really wins. If it won and took the electrons, then we'd have an ionic bond. This would become negative, this would become positive, and they'd be stuck like an ionic bond. But it doesn't do that. They just lean this way. Okay? So that means that the electrons, which are 90% probability all in here somewhere, spend more time over here than they do over here. So that's going to make this carbon partially negative, and this hydrogen partially positive. If it was full negative, full positive, this would be an ionic bond. But it's not, it's covalent. This is partially negative, partially positive. all right? But because they're symmetrical, all right, all four of these bonds are doing the same thing, but since they're arranged symmetrically, those polarities cancel each other out. Okay, so by polarity would mean we have a negative and a positive, two poles, right? Negative pole, positive pole. Earth has a north pole and south pole. Right? Battery has a negative and a positive pole. So this has a negative and a positive, negative, positive, negative, positive, negative, positive. But the symmetrical arrangement, what you end up with is a negative middle and like a positive shell around the outside, which makes it all cancel out. Okay, so symmetrical molecules are non-polar, right? That's important, okay? Let's write a statement up here. Symmetrical polar bonds make asymmetrical molecules. That's a very important statement. Okay? If you lose the symmetry, you become polar. For example, if instead of methane we had ammonia, we have trigonopyramidal. So a trigonopyramidal compound is not symmetrical. It's got a lone pair of electrons on one side and 3 hydrogens on the other side. So trigonopyramidal compounds are always polar because they lack symmetry. They're always asymmetrical. The same thing is true with bent compounds. Okay? So any bent compound will always be polar. It's never going to be symmetrical. All right, now, sometimes tetrahedral can be asymmetrical. So this one's symmetrical because all 4 hydrogens are the same. Okay? But if we replaced one of the hydrogens with, let's just say this is a carbon. Okay? If we replace this with a carbon, now it's not symmetrical anymore. Okay? So this would be an example of a tetrahedral compound that's polar because it's not symmetrical. So when you read the little chart, it says stuff like the tetrahedral down here. It says it's polar if the terminals differ. So it means if the terminal atoms are different, it's polar. If the terminal atoms are the same, it's non-polar. Okay? And that's just one way of saying symmetrical or asymmetrical. The AP exam is going to want you to say, they ask you why is something polar, the answer is because it's not symmetrical. They say why is something non-polar, the answer is because it is symmetrical. Okay? It's the symmetry that makes something polar or non-polar. So if all the polar bonds are canceling out because they're symmetrical, they're non-polar. They can't all cancel out. In this case, for example, fluorine is more electronegative than the rest of them. So the electrons are going to lean to this side of the molecule. So it gives this side a negative, partial negative. This side will be partially positive. So this thing becomes polar. The polar, non-polar stuff is extremely important. Okay? Maybe the most important thing after just being able to draw the structure. So being able to draw the structure is the most important part of all this because it determines the rest of it. If you draw the structure wrong, you're going to figure out the rest of this incorrectly. You'll be applying that chart incorrectly. Okay? As far as what's on the chart, polarity is the most important. Okay? Polarity has everything to do with everything. All right? So we'll learn in the second semester. Polar versus non-polar, some things being more polar than others, determines solid, liquid, gas, what dissolves and what, boiling points, melting points, all those things, vapor pressure, all kinds of stuff. It's all traced back to, well, this is polar and that's not polar. Or this is more polar than whatever. Okay, so very, very important thing, and it's all got to do with the symmetry of the molecule, which means to figure all that out, you've got to know the geometric shape of it. Okay, so the geometric shape of it is also very important. We want to memorize the bond angles because the college professor expects you to do that. But knowing the actual bond angle is probably the least important thing. But we still got to know. Okay. Questions about polarity? What's next on the list?
Sigma.
Sigma and pi bonds, right? What time we get out of here today? 7? Wow. Right? Yeah. Okay. All right, here comes a hand-waving explanation. My college professor used to call these hand-waving explanations. When you get talking about something that you're trying to make somebody understand, it's really complicated, you find yourself like, waving your hands around. Okay. You do that all the time. Yeah. So here comes a hand-waving explanation. All right. So single bonds, double bonds, triple bonds. That's what this has to do with. Okay. If we're going to pretend that my hands are two atoms. Okay. The center of my palms are the nucleus of those two atoms. Okay. These two atoms would like to bond with each other. All right. If they're going to single bond, okay, which is the minimum, right? They got to be at least single bonded. What's going to happen is the atomic orbital from this atom and one from this atom are going to overlap with each other. And they're going to do so in a straight line between the two nuclei. Okay? It's all going to just like that. Okay? It's just nice and in line with each other. Okay? If they're going to double bond, okay, this goes back to your question a minute ago of why the little springs are offset from each other. All right, if you're going to make a double bond, you've got an overlap in line, that's called a sigma bond, okay? And then the other orbitals are 90 degrees to these. So these are facing these this way, these are facing this way. So as they come together, they have to bend and kind of twist themselves over, and overlap. And they don't overlap in line with the nuclei, they overlap above and below it. Okay? And that's called a pi bond. All right, if you got a triple bond, then that comes together at another 90-degree angle like this and overlaps this way. And that makes a triple bond. Okay? So you've got single bond, a sigma bond. Double bond is a sigma and 1 pi. And a triple bond would be a sigma and 2 pi's, one this way, one this way. Okay? Just write that on the board. So, single bond, double bond, triple bond. That's a sigma and a pi. This is the little Greek letter sigma. Okay, just a little Greek letter. A sigma, and a pi, and triple bond is a sigma,
Sigma, pi.
and 2 pi's. Pi, sigma, pi. All right, now,
Sigma, psi.
very much like hybridization, your organic chemistry teacher is going to expect you to dig into the details of all that. In hybridization, your organic chemistry teacher 2-3 years from now is going to expect you to dig more into the details of sigma and pi bonding. At this point, we need to have first heard of it before, okay, and just be able to identify it, okay? So all we got to do is be able to count them up, okay? That's all we got to do, all right? So one of the great benefits that I hope you have when you go to college chemistry classes is that you have at least heard of whatever they're talking about, okay? There's an enormous amount of retention that happens, a difference in retention between two people when one person is hearing somebody explain something that they've at least heard of it before versus trying to gather up an explanation of something you've never heard of before. Just you're an enormous hole. You're like, I heard of what? Like, you know, that's not right. But you're like, oh yeah, I remember we heard something about hybridization, and then it's going to take 30 minutes to explain to you. You'll retain more of it. So we're just trying to give you just a little taste of all this stuff. Okay? All right, so all we have to do for our purposes is just count them up. So here we have, in this example of methane, 1, 2, 3, 4 single bonds. So that's 4 sigma bonds and 0 pi bonds.
Oh, okay.
All right. For water, you've got two single bonds, so that's two sigma bonds and 0 pi bonds. For ammonia, there are 3 single bonds, so that's 3 sigmas and 0 pi's. For carbon dioxide, there are 2 double bonds, so that's going to be 2 sigmas and 2 pi's. Each one of these consists of a sigma and a pi. Sigma and pi, so 2 sigmas, 2 pi's. The concept of pi bonding has a lot to do with reactivity of organic compounds and things like that. Again, that goes over here shortly. I told y'all my story about my organic chemistry grade. I sat down in my class. Okay, so I took organic chemistry, sat on the front row, tried to be a good student. I made a B, not bad, okay, made a B. Most people in the class either made it, so a few people made an A, there were a lot of B's, everybody else failed it, okay? Because you can kind of get it or you don't. It's like there's not really a lot of middle ground in class like that. Like my environmental science class right now, you either do it or you don't do it. You know, people with the A's and people with like 4s. So I sat there, the guy on my left made an A, I made a B, the guy on my right made an A. The guy on my left is a dentist somewhere, Birmingham or somewhere. The guy on my right is my eye doctor. Okay. All right, the guy in the middle, me, made a B, right? So I got in the PhD program at UAB and got a PhD in chemistry. You go to chemical engineering school, you teach chemistry, you do all that stuff. You be a full-fledged chemist, whatever you want to be. Probably not going to be a medical doctor. Okay? The dudes with the A's, they're medical doctors. Right? Kind of the way it works. Okay? Side note to all that is I have to change this statement a little bit now, but I used to always say it this way, that your high school grades don't mean anything. Your college grades mean everything. Okay? They changed that a little bit because they do give scholarships now for GPA since COVID. It's like the COVID year, they didn't want people taking an ACT in a room together or whatever, so they started giving out scholarships based on GPA, which is a very, very new concept. And it hasn't gone away. I think it will go away, but I don't know. I have one little conspiracy theory that says it might not go away. I'll share that later. So it might not go away, but it might go away. So if I were you, I would not be banking on my GPA to get the scholarship money, because the class of 2020 or so was the first people in the history of the world to get GPA, legitimate scholarship money from GPA. High school, that was a good thing. And have an ACT score plus 4s. It's legit. An instrument, something. Some kind of extracurricular talent for an ACT score. That's it, right? And the reason for that was because they made it nationally more, right? Where GPA means nothing in high school. I could easily give everybody 100 points. There's nothing I can do about it. I could pass out a word search every day that had words in it that are in the state course of study. And I could make a very strong argument in court if I had to, that I taught the courses out on the state course of study. And everybody would make 100. Unless it was environmental science, where people wouldn't bother to turn the word search back in. Which some of you make 100, some of you make 0. That's the easiest class in the building. By far. I teach the hardest and the easiest classes in the building. Most of that's for my own sanity. I could do 6 periods of hardcore academics. I used to could. When I was in my 20s, I could do 6 straight class periods and make everybody cry. I can't hold up to it. Why? They're 45 and not 25. When I was 25, I used to get good at it. It's hardcore. I could teach 6 periods a day without taking a breath. Not anymore. I sit down, take breaks, watch the YouTube. You're essentially Joe Rogan or something. It's 45. The problem back then when I was in my 20s was the students had to be trained to keep up with the exam on time. Point being, circle back around what we're talking about. GPA in high school, okay, high school needs to be about what you learn, okay? It's gotta be about what you learn. I've had numerous arguments with parents in 20 years about the kids' GPA because kids don't care about, never care about learning anything. It seems like very rare if you do. They always care about the grades. The shameful thing is that most parents don't care about anything except the kid's grade. They don't care if they learn anything or not. I've had so many arguments with parents in the last 20 years about that. What nobody understands is that what you learn in high school is infinitely more important. Even in getting a scholarship, it's more important. Because what good is the scholarship if you flunk out in a year, right? You're very good. You earn a scholarship to where you want to go. And if you don't pass your classes when you get there, guess what? You're out of school, right? So learning something in high school is the most important thing. So what we try to do here is give you some knowledge, okay? It may or may not let you make an A, who knows, but it gives you some knowledge, because when you get to college, then your grade 100% matters, like it's everything. Okay? Like we always said before, like you make a C in your freshman chemistry class, you're not going to med school. It's not going to happen. You can have all the extracurricular activities and be the nicest person in the world and feed the homeless, build houses for people during spring break, and do everything you want to do. You make a C in chemistry, you're not going to do nothing about it. You're the greatest person ever. You just have to be a great person who's not everything. So, you're doing good because your GPA is still on your transcript. I mean, it will help you. Like you can try it.
Can't
It
you
will boost your GPA, but it's not going to take the original bad grade off.
So we can withdraw before it.
There's a date, there's a withdrawal date, which you can withdraw with no grade. Varies from school to school, place to place, but there's always a date, a few weeks into the year. You're like, no, you gotta get out of this, but you gotta make that decision. Because past a certain date, it's gonna be posted on the transcript as, if you withdraw later on, it's like withdrawal with grades, so your grades gonna be posted. Like, if you withdraw with a D, it'll say like, withdrew on November with a D. Withdraw in like September, it's just withdrew, nobody knows why. It might not even show up on the transcript that you took, I'm not sure about that.
Was that first test? You did it? Yeah.
I only dropped one class in college, I dropped it after 10 minutes. I don't know if it ever showed up on my transcript or not.
Dropped everything.
10 minutes, yep.
How bad was it?
He asked us to write a mathematical proof of why 1 equals 1, and I got up marked out.
Wow, one, one.
You know,
I would say
he said, don't you at least want to stay around and see the answer? I said, no.
what class is this?
Advanced math. It was way more advanced than I thought. I read the little course description, it didn't seem that advanced. I walked in there and he passed out the syllabus and said, okay, our first assignment is to write a mathematical proof that 1 equals 1. And I said, no, I'm done. I walked out. Yeah, I don't want to do that.
And then 3/3, you say 1, but it also equals 1.
I just can't do that. So anyway, life lesson for today, okay? Life lesson for today. College grades matter. Only makes me think about it because we're dipping our toe in the water of organic chemistry here, okay? Which is the hardest class you will ever take if you take it. This undergraduate class.
What's the easiest? What's the least hard?
Probably freshman chemistry compared to the rest of them. It has about a 50 to 60% failure rate.
Yeah, I used to say that every time.
I was,
Yeah.
we had a 65 or something.
There you go. Where do you go to high school?
Chelsea.
Yeah, it's no joke. Organic, if you take a poll of people, if you take a poll at most universities, if they have chemical engineering will always win. It's the hardest degree to finish. And then organic chemistry will be the hardest class.
Don't become a doctor, kids.
I mean, you know, somebody's got to, but,
Right.
you know, it's rough. It's rough. But you get paid, right?
You get paid.
I mean, it's amazing to think about like your grades, and we're just not, I mean, I make good enough, and I do okay. But you just think of the difference in a lifetime of earnings between a school teacher and a dentist. Okay? An A versus a B in a teacher class would be the difference in millions of dollars. Right?
Wait, the technical students you done like research and get more money than what you make now though?
Possibly, yes, I could have had options, obviously, I chose this.
It's like, I'm pretty sure.
But it still is a general rule, medical doctors are gonna make more money than even the research scientists. All right, let's do this right quick. What was it I was going to, okay. So the quiz is Friday, that exact same piece of paper, no periodic table, no anything, okay? Reason being is this, the reason we're doing this is, first off, these are four very, very, very common substances, right? Like they're everywhere all the time, okay? So this is, probably almost everybody in here has methane gas appliances, okay? Obviously everybody drinks water. This is a very common base chemical. We don't think about this too much, but it's in all of our fertilizers, okay? You don't have this, you don't have fertilizers. You don't have fertilizers, we all starved to death about 150 years ago, okay? So the world reached maximum population like 150 years ago, and we needed fertilizer. So now we grow food in ways that nobody ever imagined. So we have to keep doing people. Obviously, a very big deal. This is what plants use in photosynthesis. So here, right? So these are very, very, very simple, but very, very common and very important substances. Therefore, the AP exam puts them in all kinds of different questions in 100 different ways. Okay? So the hardest part about the AP chemistry exam that you're going to take next year, all right, we're all going to take that class, is the time. Okay, they purposely make the test time where you can't finish it. Okay, it's designed that way. All right, they do not ever want anybody to make 100. You make 100 on that, you mess up your system. Okay, explain that here in a minute. But the way to gain that is to know what a few things that are always on it. You just memorize that. Okay, like when you read the question, what is the molecular geometry of methane? You don't need to have to take the time to draw out CH4 and count the regions and do all that. You see, oh, that's tetrahedral, circle it, move on, right? There's a few things on there that are just almost always on there, right? And we need to know that stuff. And then tomorrow, what we're going to talk about is how we can take these four basic compounds and then a few other little tricks. We can then know the geometries and angles and stuff for a whole bunch of other stuff. Just recognizing a few little patterns. Okay, that's tomorrow's class. All right, let's talk about scoring the AP exam for a second. The way they fix that test, they have experts who design these things, but they don't want anybody to get them all right. Okay, they want everybody to fall on a continuum. Okay, because if everybody, like if I give a test in here and 6 people make 100, I don't know which one of you 6 knows the most. Does that make sense? I don't really care about that. Okay, probably kind of like, I wonder, but don't really matter in high school. But AP exam doesn't want 20% of the people to max out the scale because then they don't like that. They want everybody to fall on a continuum. So out of 150,000 people, there's like 5 people that everybody might get out of the question, okay? Which is basically 0 out of 150,000, right? So you put all these people on this continuum, and then you just simply take the top whatever percentage, and that's 5. They make a 5, and the next chunk makes a 4, the next chunk people make a 3, and a 2, bottom big chunk is a 1. And that's how they grade it. Okay. That system doesn't work if a bunch of people make 100. Okay, so it normally works out to be about 75% of the right answers will get you a 5. Okay. If you get 75% of the right answers on the test in here, that's a C. Most of you nerdy kids don't like that very much. Okay, you'll be pretty upset. Right? Some of you would be ecstatic about it. It depends, right? If you make 75% on the ACT, that's a 27, which is very respectable, right? but not gonna get you a scholarship to Vanderbilt or anything, right? It's respectable, to get you in any school that you can afford to pay for, right? But it may not get it paid for, okay? So it's very different, right? So AP exam, 75% is perfect, like considered perfect, right? Like, if you make a 75 and you make a 99, nobody left much difference, you both get 5. So AP exams are graded weird.
Wait, so 75 for AP Chem will be a 5?
75% gets you a 5.
Oh, that is way lower than biology.
Oh, biology is so much
Biology
higher.
is
It's
like,
different.
you need
because-
70 something to get a 4.
Yeah, see, biology's a little easier subject.
So I made a 4.
So more people are, they put everybody on that continuum, shift everything, get that percent. It's still it's basically a percentage to it.
What do you have to make to get a qualify for AP Chem? What do you have to make to get a grade?
55.
Oh, so it's
55%.
like the same biology.
55%.
That's a 4.
65. Roughly. It varies by a couple of percentage points every year, but it's roughly 35% get a 2, 55% gets a 3, 65 is a 4, and 75 makes a 5. That's normal. It's normal. And it fluctuates. It might be 73 one year, 77.
No AP Chem, you have to make a 70 all of this.
That's
And
great.
it's like a 90
You gotta get a little more right. So it's a little easier. And there's still only usually about 55% of the people that take it nationwide make it pretty high. You can tell that they're scaling it through a system because those numbers are almost the same. Last year, I think it changed too. I think they adjusted their, rumor is they adjusted their system a little bit for chemistry last year based on feedback from colleges and stuff. But whatever they adjusted, will do the same thing now for the next 10 years or so.
You also had the amount of how many people passed the last couple of years.
It's all, you can find those numbers.
So you're like looking at all those numbers, what our chances are.
Yeah, and what's interesting is like physics are like higher passing percentages, even though it's harder. It's only really smart people.
UAB's med school program has a 5% exception rate.
There you go. That's pretty hard to get in.